and welcome to Week 5, Lecture 2 of CO 442642 Graph Theory. Today we'll be discussing surfaces. So what is a surface? So here is the formal mathematical definition of a surface. A surface is a closed, compact, connected, two-dimensional manifold. Now, if you don't know what any of that means, let's go through each definition bit by bit from topology. So what does closed mean? It means that it contains its boundary. What is compact? It means that every open cover has a finite subcover. So again, an open cover, so we're covering this space with open sets. Any open cover has a finite subset, so a subcover, still covering the space, but finite. So essentially somehow kind of like being bounded, but here's that more formal definition. Connected would be, defined in different ways, but let's say for our purposes is path connected. There exists a path between any 2 points. So that will be connected. And then what is a two-dimensional manifold? Well, more generally, a manifold has that every point has a neighborhood that's homeomorphic to Euclidean space, and the dimension is what is the space of that dimension. So here we're dealing with R2, the plane. So every point has a neighborhood, an open neighborhood that's homeomorphic to the plane. So these are the definitions that we need. So here we'll be doing a bit of topology really, or classical topology. But the key is that we'll be thinking in the future about embedding graphs on surfaces as a generalization of plane or planar graphs. And they'll actually come up when we study minors and graph minor structure theory as an important element to understanding all graphs. So that's the definition of a surface, but now we're going to go through the rest of this lecture and delve into exactly what are surfaces, what are their types. So here are some examples of surfaces. You might want to pause and think yourself of what examples do you know of surfaces. Okay, so here's probably the most basic one is the sphere. So it would be the two-dimensional sphere. That's the surface of a three-dimensional ball. So that's the sphere. What else? What's another option? Well, there's the torus, right? So every point on a torus, donut is indeed homeomorphic. It's closed, right? It doesn't have a boundary, so it contains its boundary. Connected, certainly. Compact, yes, it's actually compact. So that's the torus. That's probably the normal way you think about it. I'm going to draw it in a slightly different format, though. So here's another representation of the torus if you haven't seen this before. So here I'm going to take a square and I'm going to actually identify the top and bottom as B. And so B will represent that, and the left and right sides is A. So every point on the left is identified with the point on the right, every point on the bottom identified with its corresponding point up top. And the corners are all identified. And if you think about this, it's compact, it's closed, it's connected, and indeed it's also a two-dimensional manifold, because any point, well, certainly any point inside the square has a plane neighborhood, but actually even the points in A have kind of a half plane neighborhood on the left side and half on the right that get glued to one neighborhood. And the same for B, and the corner actually is like 4 parts, 4 little quarter plane neighborhoods. So this is actually a representation of a surface, and that surface is actually the torus. And how you can tell that here's a picture of that is you could think of kind of cutting open the torus and laying it out flat. So if you started at a point and cut around kind of the width of the donut, and then cut around again, open up the cylinder, you'd end up with this kind of cylinder, right? So you can kind of think of going between the two, right? If I identify and then I close, I'll end up with getting the torus back. So that will be useful when we talk about some of the other surfaces, this kind of more polygonal representation, they're called, where you view them as a polygon where you identify some set of edges. What about other surfaces? Well, there's the double torus, right? So you can actually kind of make larger and larger ones by adding toruses together. So here's the double torus where you have 2 holes. So that you can check that. That's also a surface. Some more exotic ones. There's the projective plane. So if you haven't seen that before, I'll give its polygonal representation. All it is you kind of have a disk and you identify antipodal points. So here you can think I have A and I have A, and I'll identify them but opposite direction. So that's the projective plane. So again, every kind of point, even the ones in the boundary, they'll have two half-plane neighborhoods that will unify into one. So this is also a surface. So that's the projective plane, and then maybe, so it's taking a Mobius strip but gluing a disk along it. So a Mobius strip is the projective plane less a disk, but this is, that would have a boundary, so we don't, and the boundary wouldn't have the correct neighborhood, so here this one is what we do to actually make a surface. There's the Klein bottle more famously, so kind of the torus, you know, the bottle where it goes in. I didn't want to draw a picture of that because I'd be terrible at it. Instead, here's a different representation. Its polygonal representation is, it's kind of like a twisted torus. So you have B and B still get identified the same, but the A's get identified oppositely. So the kind of the upper left part gets identified with the bottom right. That's what the arrows mean. Identify this way instead of that way. So you kind of twist the ends together, and that forms the Klein bottle. And then etc. So that continues on. There's all these kinds of surfaces you can make. So we have, you know, the torus, the Klein bottle, the projective plane, double torus, triple torus, sphere, and so on. Importantly, not on this list is the plane itself. The plane that we deal with planar graphs are not actually, is not actually a surface. Why? Because it's not compact. So it's closed actually, it's connected, it's two-dimensional manifold, yes, but it's infinite. It's not compact. So if you just take, kind of cover it with, you know, infinitely many, you know, lattice grid squares types, there's no finite subcovers. So the plane is not compact, but the projective plane actually is the Klein bottle, the torus, the sphere, etc. So really when we talk about planar graphs, we'll be embedding graphs in the sphere, and that's kind of equivalent if you have finite graphs. So, all right, so those are our examples of surfaces. Maybe let's now move on to talking about operations on surfaces. So how could we construct more surfaces? So generally, I'll go through a couple ways to make new and kind of larger surfaces out of smaller ones. The first way is connected sum of two surfaces. So if I had a surface sigma 1 and a surface sigma 2, I can actually kind of glue them together to make a larger one. How does that work? Well, we take two disks, one in each of the surfaces, and we delete those disks. So we remove a disk from both surfaces and you glue along the boundaries of the disk. So here you can kind of see my picture where I took two tori and I deleted and glued, and you get actually a double torus. So in this way we could make a triple torus, a quadruple torus, etc. But you could also glue two projective planes. If you do that, you actually get the Klein bottle. That might be hard to see, but that's what you get. So this is clearly a way to generally make surfaces. Because you'll see that when the gluing will create two half neighborhoods, and that'll keep the two-dimensional manifold property. If they're both compact, the result's compact, connected, so on. All right, what's another operation you can do? Here's a fun one. It's adding a crosscap to a surface. So this is actually kind of a different way to think of how you make the projective plane from the sphere, but it works more generally. You remove a disk, so you kind of delete the interior of the disk, and then now the things on the boundary have only these half neighborhoods, but then we identify the antipodal points of the boundary. And the result will, again, be a surface. So this is called adding a crosscap to a surface. And you can do this in any surface. You can do it in a torus, in a Klein bottle, double torus, etc. So adding a crosscap will get you a new surface. There's adding a handle. So that goes by, again, just dealing with one surface, but you remove two different disks and you identify their boundaries with the same orientation. So here I've kind of drawn it. So you say there's a clockwise, so here a counterclockwise, so we match counterclockwise to counterclockwise points, and this will end up, again, merging those half neighborhoods. And why is it called adding a handle? Well, maybe it's better thought of topologically as, instead of just kind of identifying, I actually add in a handle, like a handle to a mug or coffee cup. And that's equivalent, but here it'd be kind of having that handle, but without any length to it. So imagine add the handle and then pull it together and stitch it, so a zero length handle. But topologically, these are all the same thing. So you can do that. So if you add a handle to the sphere, you'd actually get the torus, right? A donut is homeomorphic topologically to a coffee cup. And so if you add more handles, i.e. holes, you get larger and larger tori. And then there's one last weird one, is adding a twisted handle. So that would be you remove two disks, but identify the boundary somehow with opposite orientation. So you kind of have your handle and you twist and you add it in. And what does that buy you? Well, if you start with the sphere, it'll end up with the Klein bottle. And we'll talk a little bit more generally what would happen. But here are, four basic operations to kind of make more complicated surfaces, starting from a smaller one. So we could add handles, twisted handles, cross-caps, or connected sums of two surfaces. Okay, so given all of that, then what are surfaces? Well, now we're prepared to tell you the answer. So this is the classification of surfaces theorem from topology. So every surface is actually homeomorphic to one of the following. So according to our current definition, so then it's only two options, really. You can be what I'll denote as SH, which is adding at least h greater than or equals to 0 handles to a sphere, or NK, which comes from adding at least, here k at least 1, cross-cap to a sphere. So you can kind of add a sphere, and you can then add either handles or cross-caps, and these get you all the possible surfaces. So that's really it. And there's a different equivalent way to think about it. If you'd rather talk about, instead of adding handles or cross-caps, you could think of these connected sum. And from that point of view, then S0 is the sphere, and SH for all h at least 1 is the connected sum of h tori, and NK would be the connected sum of k projective planes. So somehow the torus and the projective plane are the base surfaces other than the sphere, and the larger ones are made from their connected sum of tori or connected sum of projective planes. But that's also equivalent to adding handles or adding cross-caps. So that's the two ways to view all surfaces. We have these two families. But there's another important point about these families, is that they kind of come in two flavors in an even more meaningful way. So we say a surface is orientable if there exists a consistent choice of orientation and non-orientable otherwise. So you might know this, the SH, those tori in the sphere, are so-called orientable surfaces. And the NK, the projective plane, and the Klein bottle are non-orientable surfaces. So what do I mean? Well, more informally, if you haven't heard this before, a surface is orientable if whenever you walk around, the left and right remain the same. So you can kind of consistently come up with an orientation. What it really means, if you have an understanding of left and right, or clockwise and counterclockwise, and as you walk around, that always kind of remains the same. Right? So on a sphere, you can really come up with a consistent kind of orientation of coordinates. And then this also works on the torus and so on. But as you might know, with the Mobius strip and Klein bottle and such, that doesn't apply anymore. You walk around and become disoriented. So there's a more formal way to say this, is we say a curve gamma in a surface is two-sided if any small enough strip containing gamma has two components after deleting gamma, and one-sided if it only has one such component. So what you're imagining is, when we said walk around, what we really care about is when you walk around and you return to your starting point. That's the idea of getting a closed curve. So this should be for closed curves. So a closed curve gamma in a surface would be two-sided or one-sided, according to that definition. So we'd have a two-sided surface. So if you have a consistent understanding of left and right, then the left will all form into a component when you delete gamma, and the right will all form into a component when you delete gamma. Okay, so that is the curves. How does you define orientable from that perspective? Well, a surface is orientable if and only if every curve is two-sided. So if it's impossible to actually find a closed curve that's one-sided, then, and again, all these, that's typo there, all of these should be only for closed curves. So ones which return to their starting point. And so you're orientable if only if every curve is closed curve is two-sided. So that's saying, there isn't a way to walk around and return to your starting point losing this orientation. That's what it would mean to be non-orientable if you had a one-sided curve, a closed curve. So similarly, I wanted to define more about closed curves. Again, typo, that should be closed curve. A closed curve in a surface is said to be separating if the deletion of gamma disconnects the surface. So you can imagine that, if you bounded a disk, this would happen. So this would happen in the sphere, but it turns out that not all closed curves are separating. So this will happen for one-sided curves, because clearly it'll remain connected. But also, if you imagine, there can be non-separating ones in the torus. So if you have a curve that goes around kind of the donut, then that won't be separating, because the torus will still be connected from its other direction. We'll say a curve is contractible if gamma can be contracted to a point. So its equivalent way to say is that gamma is two-sided and it's separating, and at least one side bounds a disk. So you can kind of continuously deform it to a point. So that's helpful. And then lastly, I wanted one more operation on surfaces, which is instead of augmenting to make larger ones, you can think of reducing. And that can be done by what's called cutting along a curve. So if we had again, this should all be for closed curves. If you have a closed curve gamma, you delete the curve and you add a disk to each side of the curve. So if it's a two-sided, if it has left and right, we'll add a disk to the left side and disk to the right side, and that'll kind of cut it open. If it's a one-sided one, we just add kind of one disk in, and it will essentially transform a cross cap into a disk, is what's going on there. So that's called cutting along a curve, and in that way we can actually reduce surfaces. So now I can kind of sketch for you, with these ideas, a proof sketch for classification. So let sigma be a surface. Here's how you would kind of prove the classification of surfaces theorem. You'd argue that if every curve in sigma is contractible, then sigma is actually the sphere. So if everything is always contractible, the only thing you can be is the sphere. So I won't go through how to do that, but let's just say we did. So we may assume there exists a non-contractible curve gamma in sigma. And now you classify by what type this gamma is. So we consider always kind of cutting along gamma, this closed curve. So again, these should always be closed curves. So if every closed curve contractible, there would exist a non-contractible closed curve. So if gamma is separating, then we say that sigma is the connected sum of the two smaller. So if you think about what it means to cut along a separating one, it would separate into two bits. If then we did that and we glue the disks, that's inverting the process of connected sum. So then somehow if you were able to use induction, which you could do with fundamental groups or things like that, you'd realize that the two such surfaces would be an NK or an SH, and so we'd really be taking the connected sum of somehow two surfaces that we already know. So that would be if it was separating. If it's two-sided but non-separating, then what really is happening is we don't separate into two different surfaces, we just have one smaller surface, and then we add these disks. That's the inverse process of adding a handle. So this is cutting along, that would be inverting the process adding handle, so really sigma would be obtained from a smaller surface by adding a handle. And then the last option is that it's just a one-sided curve. And one-sided, of course, are never separating, and so then what you really get is you're inverting the process of adding a cross cap. So if we went back to the larger surface, we'd be taking a disk and turning it into a one-sided curve, so that would be adding a cross cap. So really you can view connected sum, adding a handle, adding cross cap. You can view those, their inverses as cutting along certain kinds of curves in the surface, separating two-sided, non-separating, and one-sided. So in this way you could essentially prove the classification theorem modulo one last bit. So if you should think about that, why are there only two outcomes? Why do we only get two outcomes, the SH and the NK? Why do we only get these two families, the orientable and the non-orientable? Let me be more precise what I mean by it. Think about the proof I'm sketching for you. You know, what happens? So we have these operations of connected sum, adding cross cap, adding handle. What happens when you add a cross cap to SH? So what if we have SH as our smaller surface and then we add a cross cap to that? What if we're adding a handle to NK? Or what if we're taking the connected sum of SH and NK, right? When we add cross caps to NK, you get a larger NK, handles to SH, a larger SH. Connected sum of two S's is an S, two N's is an N, but what about these mixed cases? What happens then? Why don't we get some weird third family, or really an infinite spectrum where we have some number of handles and some number of cross caps? So maybe pause, think about it if you don't know this, but here's the strange facts. In all the cases mentioned above, the result is always non-orientable, because the existence of at least one cross-cap will disorient the surface, right? So just knowing somewhere that there's a one-sided curve, somewhere that there's this cross-cap, we can always, then that's enough, right, to disorient the entire surface. However you walk, you could always walk through that cross-cap and disorient yourself. And what that does, this is very strange, is it means that these all become their non-orientable versions. So adding a cross-cap to SH is going to give you N2H plus 1. And adding a handle to NK will be NK plus 2. And connected sum of SH and NK will be sorry, that's a typo, that should say 2H plus K. So why is that? Because the disorientation turns every handle into a twisted handle. And a twisted handle is equivalent to adding two cross-caps. So a twisted handle is really like adding a Klein bottle, and that's actually the same as adding two cross-caps, or two projective planes, if you would. So that's kind of just an amazing fact that really when you combine the torus and the projective plane, there's only one outcome, and it's the same as combining the Klein bottle and the projective plane. And it's the same as taking the connected sum of three projective planes. So I won't try to prove that to you. It's not too hard, because you could take, you could just try to show that the torus plus the projective plane, if you cut along a certain kind of one-sided curve in that one, you'll actually end up getting the Klein bottle instead of a torus, would be the proof. But that establishes those outcomes, so that establishes the classification theorem. And this brings me to our last topic for today, which is Euler's formula for surfaces. So now that you know about the two families, and maybe you see that a handle is worth two crosscaps, it makes sense to define what's called the Euler genus of a surface, which I'm going to denote G of sigma. Sigma is the surface, and that will be 2H plus K. So it will be 2 times the number of handles plus K the number of crosscaps. This puts handles and crosscaps on equal footing and allows you to compare non-orientable and orientable. So in topology, sometimes they refer to the genus of the surface, but only care about orientable ones, and sometimes then they let that be H, just the number of handles. But if you want to make them comparable, really you should do 2H plus K, because then it'll have the same Euler characteristic. And then you get Euler's formula for surfaces. So here's just more generally how it works. If G is a graph embedded in a surface sigma, then V minus E plus F, where F is the faces again, is equal to 1 plus C, where C is the components, that's their old thing, minus the Euler genus. So the Euler genus of the sphere is just 0, so that would give you the Euler's formula for the plane graphs. But here for graphs embedded on surfaces, we actually get this extra minus genus term. So I won't prove that that's similar to the proof for Normal's Euler's formula for the plane. But that's nice, right? So you get 0, and then you get 1 for the projective plane that you're subtracting, and then more generally the genuses. So you get 2 for the torus, and 2 for the Klein bottle, 3 for N3, and onward. So that's Euler's formula for surfaces, and in the same way as you do for Euler's formula plane, you can convert this into a bound, for example, on the number of edges in a surface. Graph embedded in a surface is upper bounded by 3 times, you know the 3V minus 6 for planar graphs, but you actually get 3 times V minus 2 plus G, where G is the Euler genus more generally. So graphs that actually embed on surfaces actually have a few number of edges. They're relatively sparse. Now granted, every graph will eventually embed on some surface, and maybe next time we could talk about that, because you can just add handles that will end up, you could kind of draw it on the plane and then add handles, and then you'll be able to end up embedding it. But generally, if they're rather large ones compared to the genus, then they'll be rather sparse and only have like a linear number of edges. So that's about all I wanted to talk today. We'll pick up next time when we then talk about coloring graphs on surfaces and generalizing kind of the four-color theorem to that, and what's more generally true, and maybe some about list coloring as well. So that'll be our last talk on coloring. We'll be talking about coloring graphs on surfaces, and then we'll be moving on to minors in the future. So until next time, see you then.